So this is the second topic in Unit 8 for logs. It is the key characteristics of logarithmic functions. So if we look at this, we have our general form. We have our a value, which is our coefficient, and then we will have the b represent the base, and then our x will represent the argument, okay? So this is where a and b are constants. A cannot equal 0 because then we don't have, it just goes away, and b cannot equal 1. Basically, what this means is if our b is equal to 1, there's nothing that we can raise 1 to the power of to change it being 1. So no matter what x is, that will always be 1. So if you have like log 1 of anything, the output will always be 1. So we just end up with a straight line, which means we are no longer evaluating a log, we're just evaluating a constant. Okay, so that's why that restriction is there. And that someone in class actually cleared that up. I was trying to describe it graphically, but I forget what student it was. It was in either third or fourth period. So thank you for that if you end up seeing this. So as far as the logarithmic functions, we have an example where a is greater than 0, so it's positive, and then b is greater than 1. Our base will always be, in this class, we'll see the base be greater than 1, okay? So when both of these characteristics exist, we will have a function that is increasing, okay? So this is increasing and concave down. And when the function is concave down, that means the rate of change is decreasing. Now in exponentials, we had a horizontal asymptote. Now for logs, we'll have a vertical because they are inverses, which we will touch more on in the last unit in this semester for unit 10. Our vertical asymptote will be at x equals 0. So same characteristics as exponential functions. Logs are always increasing or decreasing, meaning they are also monotonic. So because it's never changing, whether it's increasing or decreasing, we have no extrema. And then same thing with concavity. Logs are always concave up or concave down. So this means no points of inflection. And if we look at this graph up here, this is a case when b is greater than 1. Again, for the bases, we'll see integers. Bases will be provided as integers. There will be problems that you solve where your base might not be an integer, but it will still be positive, okay? So when a is less than 0, that's going to give us let's write it out like this. It's going to give us a vertical reflection, okay? So it's going to reflect over the x-axis. So thinking about your transformations from unit 1. So now our function is decreasing and it's concave up. And we still have that vertical asymptote at x equals 0. All right, so this one is, the function is decreasing and concave up. And because it's concave up, that means the rate of change is increasing. So in this course, we relate the change and the rate of change to concavity only. All right, so now in behavior, this is going to be similar to exponentials. So let's say that we have this function here. a log function where a is greater than 0 and b is greater than 1, we can say as the input values. Actually, let's make this specific to logs. So as the input values approach 0 from the right, the output values decrease without bound. So with exponentials, we did not have our domain interrupted. There were no restrictions on the domain. So our limits could either go to infinity or negative infinity. But now with this vertical asymptote restricting our domain, we have to be more specific with our limits. So if I want to talk about the left limit for the function I drew up in the corner, it's not going to negative infinity anymore. X is approaching 0, but specifically from the right. And when I say from the right, I'm talking about on the right side of this vertical asymptote, okay? So it's not really about where you're traveling from, it's about where you're traveling to. So the left side of our function is approaching this vertical asymptote from the right side of it. There's nothing on the left side unless we apply the appropriate transformations, okay? So we have to include this superscript and be very specific about, okay, where are we approaching this asymptote from, okay? And I'll call this little doodle here f of x. So we'll say f of x, and it's approaching, it's going down, so it's going to be negative infinity. So that's what you'll see over here is now we have that x is approaching 0 from the right side or from the positive side of that vertical asymptote. Okay, so now we have 3 examples. It says write the limit statements for the end behavior of the following exponential functions, and determine if the exponential function is increasing, decreasing, and concave down or up. So that should say log, not exponential. Sorry about that typo. I did not catch that in class. I don't think anybody else did either. We don't read instructions well. Me neither. Okay, so this is a log function, and we can tell because there's a vertical asymptote. And it's going to be at x equals 0. So the left limit statement is referring to the left side of my function, and that's the side that's approaching the vertical asymptote. So the limit as x approaches 0 from the right side, we'll call this f of x. I didn't label it. And it's going down. We want to use the outputs, so it's approaching negative infinity. The right limit statement is going to be the right side of the function. So we have the limit as x approaches. The x values are increasing without bound. There's no restriction on the domain in this direction. So it's approaching infinity for f of x. It's not increasing, the rate is not increasing as much as an exponential function, but still there are no barriers for this. It's still going to be increasing to infinity, just not as fast or as quick as an exponential function. So we'll still say approaching infinity. Concavity, it is concave down. And the function, increasing or decreasing, the function is increasing. Now, the rate at which it's increasing is slowing down. We can see that because it's concave down. But if you ever need to just make sure, okay, how do I know this function is increasing? Well, look at the slope. Or just draw a tiny slope line. We can see that if I were to draw this as a linear function, the slope would be positive because it's going up, okay? So you can always test it by just drawing a little slope if you're not sure. All right, part B. G of x is in part C, so let's call this one h of x. So h of x, we still have that vertical asymptote at x equals 0. There we go. And I'm just going to label it just to be consistent. And the left limit statement. So the limit, as x approaches, we're approaching the vertical asymptote again, still from the right side, for h of x. Now the function is increasing. It's going to be going up. We use the y values, so it's going to infinity. The right limit statement, because this has been reflected, it is now decreasing, so the output values are going down. So the limit as x approaches infinity for h of x is approaching negative infinity. So this function, I don't know what it is exactly, but h of x is equal to some negative a log base b x. And I can tell because we have that vertical reflection. Because of that reflection, it is now concave up, and the function is decreasing. So if I ever want a question, like I can draw a little line, I can see that if I were to draw this as a linear function, this little slope line, it would be going down, which means the slope would be negative. Therefore, the function is decreasing. All right, now we're not given the graph. I always suggest if you have to analyze a function, try drawing its graph. So this has a positive a value, so that means it's increasing, and we still have that vertical asymptote at x equals 0. Left limit statement, the limit as x approaches, the left side is approaching that vertical asymptote, so 0 from the positive side for g of x is approaching negative infinity. So again, use the y values for the right side of this limit statement. Right side limit statement, again, no restrictions. So x is increasing without bound to positive infinity. For g of x is approaching positive infinity. So this is, it's exactly like letter A. It is concave down, and it is increasing. All right, next we have our tables. It says select values of the several logarithmic functions are shown in the tables below. For each table, find the value of the constant k. So we also did this for exponentials, and we would look at the outputs, because for exponentials, we had equal length input value intervals. Okay, now logs are the inverse of exponentials. So that means our x and our y's are going to switch, which means our inputs and outputs are going to switch attributes. So now for tables that involve logarithmic functions, you're going to have equal length output value intervals. So with our exponential tables, we would focus on how the outputs were changing. For your log tables, you have to focus on how the inputs are changing, okay? So you're going to look for that ratio and how it relates with the inputs. Now, this tells us that it is a log function, so it has to have that relationship, okay? So let's take a look at this one. We have the equal length output value intervals. We see 1 to 2 to 3 to 4 to 5. And then now we need to focus on the x values and see how they are changing. So we go from 1 to 2, 2 to k, k to 8, 8 to 6. I can see that these are changing by multiplying the previous input by 2. So times 2, I get 2. Times 2, we get k. Times k, we get 8. Times 2, we get 8. And then times 2, we get 16. So if I see the relationship here and here, then it has to be true for all of them, okay? So to find k, I can do 2 times k. 2 times 2 is equal to k, which is equal to 4. I can also work it in reverse. I can do 8 times the reciprocal, which is 1 over 2, is equal to k, which is equal to 4. All right, this table, we have K, 6, 18, 54, 162. Hopefully from here, you can see we can get to 6 by multiplying by 3. Same relation here, same relation here, and then we can also use that to solve for K. So we do have to work backwards this time. So we'll have 6 times, we're going to multiply with the reciprocal, aka divide by 3. That's going to be our K, so we get 2. This one's a little more tricky, okay? So there really is not one single operation that can connect the value of the inputs, okay? So my suggestion is try multiplying by 2, then by 3, maybe 4. And if that's not working, you're going to have to either add or subtract after you multiply, okay? So let's try multiplying by 2 and maybe subtracting 1. So I can do 4 times 2 is equal to 8. Minus 1, I get 7, okay? Now, if I want to get to 5, I can do 4 times 2 is equal to 8, and then subtract 3 to get 5. Let's try that again. So I'm multiplying by 2, and then I'm subtracting 3. So let's do it with 5. So I have 5 times 2 is equal to 10, minus 3 is equal to 7. So if it works for 2, then we know that it's going to work for the rest of the table because it's logarithmic. They're not asking us, is this a logarithmic function? They're telling us what it is. So we just have to find that ratio. And if we found a process that works for 2 pairs, it will work for the rest of them. So we'll have 2x minus 3, 2x minus 3, 2x minus 3, 2x minus 3. And the x is going to be the input, the corresponding input. So we have multiple ways that we can solve for k. We can plug in 7 and solve for k. Or we can plug in k here and then set that equal to 19. So we'll do both. So we'll do 2 times 7 minus 3 is equal to k, which is equal to 14 minus 3, which equals 11. And then let's try the other one. So if I plug in k as my input, I have 2k minus 3, and that is going to be equal to 19. Whoops. So now we have 2k is equal to 22. We'll divide both sides. We get k is equal to 22 over 2. Therefore, k is equal to 11. So we found it. So because it's logarithmic, either one of these will work. All right, now let's try this one. So this one, it's easier to see. Like, we can find the ratio, but it's easier to see what's happening within, let me just move this over here, within the inputs. So I can see here if I add 3, I get the next one. If I add 3, I get the next one because that's 1. So we're adding 3 to our exponent. So how can I write this as multiplying? Because it's log, we have to find a ratio for our inputs. I can multiply e to the 7th with e to the 3rd, and then we have our properties of exponents where e to the 7th times e to the 3rd is equal to e to the power of 7 plus 3, which gives us e to the power of 10. Okay, and if it works for this pair, then it's going to work for the other pairs. So the common ratio is e to the power of 3. So if I want to solve for k, I'll do e to the 1 times e to the power of 3. Go ahead and put an x in there. And properties of exponents, we're going to add them together. So we get e to the power of 4, which is equal to k. Now you can also work backwards. So we can have e to the power of 7 times, I can use the reciprocal 1 over e to the power of 3, which equals e to the power of 7 over e to the power of 3. Properties of exponents you can subtract, so you get e to the power of 4 again. I feel like everyone's going to use this, but that's fine. Hopefully you don't see k here, but it's easier to see the subtraction rather than multiplying with the reciprocal. All right, says find the domain and range of the following logarithmic functions. So we have 2 log base 3 of x. Again, suggestion is draw a quick sketch. This way you have something visual to come back to, and you don't want to forget about your vertical asymptote. So for our domain, we have non-inclusive at 0 to infinity, or you can do x is greater than 0. Range is going to be all real numbers, or negative infinity to positive infinity. You could see either one. You can use either one. All right, g of x. A couple transformations occurring. That's why we want to do a sketch. If we look at this, our vertical asymptote was shifted to the right by 3 units. So it's at x equals 3. And we also have a vertical reflection. So now instead of increasing, it's going to be decreasing. So we are flipping the curve. All right, so our domain doesn't change. It'll still be 0 to infinity, or x is greater than, oh, that's a lie, that domain or that horizontal translation. So it's 3 to infinity, or x is greater than 3. Sorry about that. No matter what transformations occur for a log, the range will always be all real numbers, or negative infinity to infinity. Lastly, we have 8 log of 2x plus 3. Think back to Unit 1, where if we truly want to see a transformation, we need to isolate the x. So this would end up, if we factor a 2 out from both of these terms, we get 2 times x plus 3 over 2. Another way to do this is you can just set the input equal to 0, because we can't have an input of 0. We cannot raise any number to any power and get 0. That's why there's a vertical asymptote there, okay? There's no power that you can raise a value to get 0, okay? So if we set this equal to 0, we can find out where that restriction is. So 2x plus 3 is equal to 0. We get x is equal to negative 3/2. This method is also nice because you don't have to question the sign as long as your algebra is correct. For the transformation up here, you need to remember that it's flipped. The inputs will be the opposite, okay? So if I do a quick sketch, I have my vertical asymptote at negative 3 over 2, or 1.5. And my curve, the 8 has a huge vertical stretch, but it doesn't flip it. But again, this doesn't change the trend for the domain and range anyway, so we'll just go like that. For the domain, it will be from negative 3 over 2 to infinity, or x is greater than negative 3 over 2. The range will be all real numbers again, or negative infinity to positive infinity. I believe that is it. All right, yeah. The next video will be on residuals. I hope this was helpful.